Okay, I've gotten a few questions about integrating with partial fractions when you have this case of the irreducible quadratic factor. And there's a couple complications that can come up with this. So what I'm going to do is work through a few examples illustrating what I think is the best way to approach each of these. And the first problem happens when the leading coefficient is not 1. What's the best way to handle that? So for instance, this example here, we're integrating 1 over 2x squared minus 4x plus 9. What I would do in this case is simply factor out the leading coefficient in the denominator. So if I factor out a 2 from the denominator, now I'm going to have 1/2 the integral of x squared minus 2x plus 9/2. And now I can go ahead and complete the square as we've done before. So because I have that leading coefficient 1, I can look at these two terms here. I take half of 2, which is 1, and square it, which is 1. I'm going to add that and then subtract it. So now I have 1/2 the integral of x squared minus 2x plus 1 plus 9/2 subtract 1. So whatever I need to add here to complete the square, I have to subtract it back off. I'm going to rewrite this as a perfect square trinomial. So it's a x minus 1 squared. And 9/2 minus 1 is 7/2. So plus 7/2. Now, because I'm going to be using the inverse tangent formula, I'm going to write this as something squared. So I need to take the 7/2 and square root it. So I'll write it as square root 7/2 all squared. We don't necessarily care about rationalizing denominators because we're not in high school algebra anymore. Okay, now the nice thing once I've done this is exactly the form of the inverse tangent integral. So just a side note here, just to remind you, the integral of du over u squared plus a squared is 1 over a times the inverse tangent of u over a. So this one is a little bit trickier to remember than the normal one because we're used to just 1 over x squared plus 1 is inverse tangent. So this is saying if you have the constant term is not 1, but it's something squared, then you have to divide by that something outside and inside the inverse tangent. That's the best way, I think, to remember that. So going back to our example over here, because it's x minus 1, if we were to do a u substitution on this and let this be u, then our du would just be dx. So we can just integrate this like normal and not worry about any funny factors or anything that we have to do. So this would be 1/2. Okay, now this is my a, the square root 7/2. I need to divide by that, or think of it as multiplying by the reciprocal. So the reciprocal of root 7/2 would be root 2/7. And then inverse tangent, and then I need inside here a root 2/7 times x minus 1. And this is basically it. I'm just going to rewrite it a little bit. So let's write it as, what do we got here? We got a root 2 on the bottom. So I'm going to say that's 1 over square root 14 times the inverse tangent of, I will rationalize this, I guess, and say that it's square root 14 over 7 x minus 1. That's not really the most important thing. I could have just left that like that. And this is the final integral here. Okay, let's look at the second kind of problem, which I think is even more confusing for people, is what do you do when you have the linear and the constant term in the numerator? How do you go about splitting that up? Because it's real common for people to just kind of split it up by the linear term and the constant term, but that's not actually the way that you want to do it. So let's look at an example of that. So in this integral, we do have a leading coefficient of 1 in the denominator, so that's nice. But we have these two terms on top, x plus 10. A real common mistake here is to try and just think that I can split this up just as x over the denominator plus 10 over the denominator. That's not quite going to be what we want to do, though. We know that this is going to split up as some kind of natural log and then some kind of inverse tangent. So let's look at this denominator. If I was to let this be u, what would du be? That means that du would be 2x plus 5. So I know that I need a term of 2x up here if I'm going to kind of construct my du. I'm trying to manufacture du here. But it's x. So what I'm going to do is a little trick here. I'm going to multiply and divide by 2. So I'm going to just put the 2 inside there. Of course, I can't just multiply by 2. I have to divide by 2. So I'm going to get 1/2 the integral of 2x plus 20. See, I'm multiplying by 2, divide by 2, over x squared plus 5x plus 25. Okay, but I only need the 2x plus 5. Now this tells me how I split it up. You want to split up the 20 into 5 and 15. In other words, I'm going to split it up as 1/2. Then I'm going to have the integral of 2x plus 5 over x squared plus 5x plus 25. Plus, and then I have just the 15. So 15, this. And now, this one, the second one, is probably pretty similar to what you remember from class because you just complete the square as usual, which we did in the last one. So let's go ahead and do that. So all of this here, if this is u, this is exactly du. Okay, so it's the integral du over u. So we know that this is going to be natural log x squared plus 5x plus 25. And you can always put the logarithms here in parentheses instead of absolute value because they're irreducible quadratics. They're always going to be positive. I'll distribute the 1/2. So we got 15 halves. Okay, and now I complete the square. I take half of 5 is 5 halves, and then square that is 25/4. Yuck. Okay, so x squared plus 5x plus 25/4 plus 25, and then I have to subtract off 25/4. Okay. So this is a perfect square trinomial. And we'll write it as x plus 5 halves all squared. And again, this now is going to be, 75/4. But I want to think of the square root of this. So the square root of this, since 75 is 25 times 3, that's going to be 5√3 over 2. So it's the square of 5√3 over 2. Okay, now we're set up to do this inverse tangent. Remember the inverse tangent? So this piece here, this is just going to carry on. So this piece here will be 15 halves. Now, I would want to be dividing by that. This is a. Think of it as multiplying by the reciprocal. So 2 over 5√3. And then I have to also do that inside the inverse tangent. So inverse tangent of 2 over 5√3 times, and now it's the x plus 5 halves. Again, because it's linear coefficient 1, I can just do it like normal. I don't have to worry about any funny constants. Okay, let's put everything together. If you look at all these, we got 2's. So we're left with 3 over √3, which just reduces to square root 3. So the entire coefficient out in front here is square root 3. And then what I'm going to do here is put the 2 and just distribute it across here. That's really the best thing I can do here. So what I end up with at the end is 1/2 natural log x squared plus 5x plus 25 plus a square root of 3 times inverse tangent of 2x plus 5 all divided by 5 square roots of 3. Not very nice, but there it is. Okay, so that's how you handle splitting up into the 2. Now, let's try one where we have both problems. We'll put both problems together. If you've understood the previous 2 examples, you should be able to try this on your own and do it, but I'll work through it as well. All right, so this is one that typically freaks people out because it's an irreducible quadratic, but the leading coefficient on the quadratic is not 1, and it's 2 terms on top. So this seems like there's so much going on. What am I going to do here? So just calm down. Let's look and just go through the steps that we went through in the previous 2. So look at these first 2. At least this is the way that I do it. If you watch other videos, you'll see them do it slightly different, but I think this is the easiest way to do it. Let this entire thing be u. What would my du be? So I'm trying to manufacture the log first and then clean up everything up afterwards. That's the whole kind of key to this idea. So du would be 6x minus 2 dx. So I need a 6x minus 2 on top. Well, I've got 12x. That's twice as much. That's fine. I'm just going to factor 2 out. So in the previous one, what I ended up having to do was kind of multiply by 2 and then divide by 2. I guess here you could say that I'm multiplying by 6 and dividing by 6. But in any case, I know I want it to be 6. So I'll just take out a 2 and then I'll leave 6 left over. So 2 times the integral of 6x minus 5/2 over this. Okay, but I need a minus 2. Okay, so when I'm going to break down the minus 5/2 into minus 2 and minus 1/2, right? Because 5/2 is 2.5. So now I've got 2 times the integral of 6x minus 2 over this quadratic. And then we've got the minus 1/2, the integral of just the quadratic. And now this last integral here, we can do like that first problem. We can take care of the 3 like we did before. Okay, this is the key step for me. Okay, this, because we constructed it this way, this is just du over u. So this is just going to be 2 times the natural log of that irreducible quadratic. And then if I distribute the 2, it's actually just minus the integral of this. Now, remember our trick was to factor out the 3. So we're actually going to get minus 1/3 the integral of x squared minus 2/3 x plus 4/3. Okay, so can't be afraid of fractions too much. So let's see what happens here. If we're completing the square on these 2, we'd take half to get 1/3, and then we'd square it to get 1/9. So 1/9 is going to complete the square here. Again, the natural log term is done, so I'm just focusing on this integral. So let me rewrite this as x squared minus 2/3 x plus 1/9 plus 4/3 minus 1/9. Whatever you add, you have to subtract. That's a math rule. Okay. Okay, now I'm going to write this as a perfect square trinomial. This is x minus 1/3 all squared plus, now, what is 4/3 minus 1/9? That's going to be 12/9 minus 1/9. So that'll be 11/9. So this is all 11/9. But again, I want to take the square root of this, and that would be root 11 over 3 all squared. And now this piece is perfectly set up for my inverse tangent. So it would be minus 1/3. Again, I multiply by the reciprocal, 3 over root 11, inverse tangent of 3 over root 11, x minus 1/3. The 3's cancel nicely there, and the 3 distributes across nicely here to make 3x minus 1. So see, once you practice this a little bit, even the worst kind of one like this is doable. Now we can put everything together. We've got the log term up here. So twice natural log of this stuff minus 1 over square root 11 inverse tangent of 3x minus 1 all over square root 11. Okay, and that is about as bad as it's going to get for the irreducible quadratics raised to the first power. Now, what if it's squared or cubed? Now, hopefully your teacher's not a masochist or sadist. But if you have that, you just do the same kind of thing, right? You are going to manufacture, it's not going to be a natural log here, but you're manufacturing the u substitution so that you get, like u to the -2 or u to the -3 or whatever it happens to be. And then you have your term that you don't like to deal with. And probably the easiest way to do that is to do another u substitution and use the reduction formulas like we had in the course packet. So those are never easy, but still, that would be the best way to handle those higher powers of the irreducible quadratic. So I hope this helped you with these ones. This is definitely the trickiest kind of examples for the partial fractions cases. So if you can do this, then you can probably do all of the partial fractions. Okay, talk to you later.